Okay, welcome to the video on exercise 7J, page 347. So this contains two new ideas, and so I'm going to do questions 1, 2, 3 and 5. So again, I'd like you to turn to page 347, I'd like to read through question 1, have a go at it, pause the video, and then I'll do the question. Now, when I say have a go at it, try to do something, at least write something down on the page. One of our problem solving strategies is if you can't think what to do something. So there we are. Here we are. So we're told that the probability that B equals B is given by a formula, and the formula is K times B minus 4. Sorry, 4 minus B. That's the formula. And B is equal to 0, 1, 2, 3. Now remember, B, the lowercase, are specific values of the random variable capital B. Capital B is the set of all possible values of the random variable. And remember, the idea of a random variable is a variable whose value depends upon chance. So it's basically, we can't predict what it's going to be. But it tells us here that B is 0, 1, 2, 3, 4. Remember, this idea of a discrete probability distribution, all it is that with the probabilities in. Sounds complicated, but there we are. And this is the probability that capital B equals lowercase b. So we need here the probabilities of each of these items, and we're told that we're going to use that formula in order to calculate. Now we don't know K, but remember in maths we're not worried about extra letters here and there, we just do what we would ordinarily do. So we can't find out the actual probabilities at this stage, but we're just going to substitute into here. So the probability for 0 is going to put a 0 here. So this is going to be K times 4 minus 0. This is the B, is 0. So all I've done is replace that B with 0. Here I'm going to replace the B with 1. So this is K times 4 minus 1. Here I'm going to replace the B with 2. So that's 4 minus 2. This is K times 4 minus 3. Now, we don't want to leave it like that. So that then becomes 4K. This becomes 3K, and this becomes 2K, and this becomes K. Now, one of the things straight away that should come to your mind is as soon as you see a probability distribution, discrete probability distribution, you need to know that all the probabilities must add up to 1. So straight away we can say, look, therefore, or this implies 4K plus 3K plus 2K plus K equals 1, 10K equals 1, K equals a tenth. Now when you get to that stage, okay, we can say this must be 4 times a tenth. So let's write out that probability distribution again with all the values in, just to make sure we're not put off by the complexity here and the working. This is the probability that capital B equals lowercase b. If K is a tenth, you've got 4 times. Remember, a number next to a letter is multiplying, so 4 times a tenth. So I'm going to keep them all as tenths. 4 tenths. 3 tenths, 2 tenths, and 1 tenth. And we're checking that we've done it right because we get 10 tenths, they all add up to 1. So that's the first part. It says find K and E of B. Now what is E of B? Well, E of B, let's say E of X. E is the expectation or the mean. So just as you can have, remember this is a probability distribution. Just as in statistics, remember the idea between statistics and probability. Statistics describes what has happened, probability describes what might happen. So in the same way that you can get a mean of a probability of a statistical distribution, you know how to calculate the mean, add them all up, divide by how many there are, or you might do the same thing in a frequency table. Then in a probability distribution, we have the expectation. So it's basically saying, it's kind of like, we call it the mean, but it's kind of like on average, what are you going to get, which one of these, say, is the average, or where is the center of the expected value? What's the expected value? And the way we do that is very simple. Expectation of X is just the value of X, each of the X, so we add them all up. We do each of the values of the outcomes multiplied by the probability of that value. So all we're doing, I mean, you don't need that formula, but so it's very straightforward. E of B is just that times that, plus that times that, plus that times that, plus that times that. That's all you do. If you ever talk about expectation, just multiply the outcome by its probability. So 0 times 4 over 10, plus 1 times 3 over 10, plus 2 times 2 over 10, plus 3 times 1 over 10. That then becomes 3 over 10, plus 4 over 10, plus 3 over 10, which is 10 over 10, which is 1. So the expectation is 1. Okay, so I'm going to move on to question 2. So again, that's on page 347. I'd like you to pause the video, go to question 2, and have a go at it, and then come back and I'll do that for you. So this is question 2. Apply your probability distribution table from exercise 7i, question 4, to find the expected number of male births in a set of triplets. So if we go back to exercise 7i, question 4, you will see that's the one about the genders of the 8 possible genders of triplets, and it gave all the possible ways of doing it. So if you remember from that, we had the number of males. Well, we actually did it for females, but because it's absolutely balanced, you know, it's 50% of each, it doesn't matter. So the number of males can be 0, 1, 2, or 3, and the probability that capital M takes the specific value M, this was 1/8, 3/8, 3/8, and 1/8. Okay, so question 2 is saying, find the expected number of male births in a set of triplets, and we're given the information that the probability of a female being born is 0.5 and the probability of a male being born is 0.5. So we're getting three births, so we've got triplets, and the number of males can be 0, 1, 2, or 3. So just apply your thinking to that. Okay, this is called the expectation, the mean of a probability distribution. So how many are you expecting? Ask the simple question. You got 3 babies, how many are you expecting to be male on average? This is the expectation. Doesn't have to be a whole number. So again, very, very straightforward. So the expectation of M, all we're doing is that times that, plus that times that, plus that times that, plus that times that. What do you think the answer is going to be? There we are. So 0 times an 8, plus 1 times 3/8, plus 2 times 3/8, plus 3 times 1/8. That's 0, that's 3/8, plus 6/8, plus 3/8. Altogether that's 12/8, which is 1.5. Now of course that doesn't make sense in the context of a single set of triplets, but it's 1.5, and it's what we'd expect, isn't it? If it's exactly equal chance of female and male, then we're expecting 1.5 over that many. Now of course we're going to use that in the context of, say, 100 triplets being born, then 150, and it makes sense in that. But our expectation doesn't have to be one of the actual values, just as when we do the mean of a data set in statistics, the mean doesn't have to be one of the data values. It's often not one of the data values. So again, we're happy with that. So that's the expected number of males is 1.5. Okay, again, so I'm going to do question 3, so I'd like you to pause the video. I'd like to go to question 3 on page 347, and then have a good go at it. And again, this idea in maths, if you're not sure what to do, do something. At least read through the question fully and have a think. Sit there for a couple of minutes. If you're not sure what to do, sit there for a couple of minutes and at least think about it before watching me do the question. Okay, have a go yourself. Okay, question 3, let's read through it. A handbag contains 7 coins and 3 keys. 2 items are taken out of the handbag, one after the other, and not replaced. And so whenever you see the word replace, you need to be thinking, that's one of your key words there. Find the expected number of keys taken out of the handbag. So let's have a go at this. Now, in this question, it doesn't tell you what to use, But remember, at GCSE we're commonly faced with these ideas of green beads and red beads in a bag, and we commonly use a tree diagram. So I'm going to use a tree diagram for this one, and we're assuming that choosing a coin or a key is equally likely. That's assumed in the question. And so if we do the first selection, we've got 7 coins and 3 keys. So this is going to be coin and key. And so there's 10 items altogether. So that's going to be 7 out of 10. And that's going to be 3 out of 10. And then when we do the next choice, so this is the first selection. That's the first, and this is the second. So if the person chose a coin to start with, then there's only going to be 6 coins left, and there's 9 items. So that's 6 ninths and 3 ninths. And then if the person chose a key first, there's only 9 items left, but there must be, this is the coin and the key, so there must be 6 coins out of, so there's still 7 coins left, so 7 out of 9 there, and 2 out of 9. I guess check with any tree diagram, you're checking that if you've got 2 here, they both add up to 1. There we are. So we can see, remember when you do a tree diagram, you're multiplying along the branches, so the probability of getting a coin and a coin, or we can say, coin, probability of coin is 7 out of 10 times 6 out of 9, which is 42 out of 90. The probability of coin key is 7 out of 10 times 3 out of 9, which is 21 out of 90. And the probability of key coin is 3 out of 10 times 7 out of 9, which is 21 out of 90. And the probability of KK, 2 keys, is 3 out of 10 times 2 out of 9, which is 6 out of 90. Now don't simplify these at this stage. Normally with fractions you always simplify them, but I'm keeping them like that so I can just quickly add up 42, 84, 90 out of 90, we've got 1. So I've made sure that I'm not making a mistake. So these are all our probabilities. Now let's see what the question says. It says find the expected number of keys taken out of the handbag. So in order to do the expected number of keys, we need the probability distribution for the number of keys. So the number of keys, you can see here, we've got no keys here, we've got 1 key in both of those, and we've got 2 keys. So the number of keys can be 0, 1, or 2. So we'll put this, find the expected number of keys here. So we'll have key as lowercase. This is the probability that the random variable k, the number of keys, takes the specific value lowercase. So what's the probability that there's 0 k? So this is 2 key, 1 key, 1 key, so that's only that one. So that's going to be 42 out of 90. 1 key is both of these. So we have to take both possibilities. So that again is 42 out of 90. And 2 keys, there's only that one there, which is 6 out of 90. So the expected number of keys is that times that, plus that times that, plus that times that. So expectation of k equals 0 times 42 over 90. Now I encourage you here that even though we've got 0 times 42 over 90, I want you to put that down because that demonstrates that you understand how to calculate the expectation. Plus 1 times 42 over 90 plus 2 times 6 over 90. So that then is 42 over 90 plus 12 over 90, which is 54 over 90. Divide top and bottom by 18 gives 3/5. So the expectation for the number of keys is 3/5. Okay, that's question 3. Now, if you look at the next question, question 4, that's actually very, very similar. So I'm going to leave you with that because you basically in question 4 you're going to do the same thing, perhaps a little bit more tricky. But there we are. There's the answer to question 3. I'm going to move on to question 5. So if you want to pause the video, have a go at question 4, check that's right. But I'm going to go on to question 5. So please have a look at question 5 and again, pause the video, try it yourself, and I'm going to do the answer now. Okay, question 5. So this is the extra little bit that we've got in this one. We've got a game, so a spinning arrow rotates and stops one of the regions A, B, C as shown. Alexandra proposes the prizes shown in the table like this. So the letter A, this is the letter A, B, C, D. And the prize. I'm not going to put the prize in dollars because it just makes it more tricky. So the prize basically in dollars. And so 3, 7, 5 and 2. So in these games, justify whether it's fair or not. So in these questions, this is the actual outcome, the prize. So we need another table here to say what the probability is of the letter. So if this is letter L, so the probability that L equals L, and this letter would be our L. But basically, we need to look at what the probabilities are of it landing on 3, of it landing on 7, of it landing on 5, and landing on 2. And it's the prize that we multiply by the probabilities, because obviously we can't multiply A, B, C, D. They're not actually the outcomes. These are the actual outcomes. Okay, so here we are. We've got that. If you look at that circle, you can see that D is half of it. So D has got to be a half. And C is an eighth. B is also an eighth. And A is a quarter. And if you add those up, you get 1. So that's fine. So we're going to do, so the expectation of L, the overall expectation is 3 times a quarter plus 7 times an eighth plus 5 times an eighth plus 2 times a half, and that's 3 quarters plus 7 over 8 plus 5 over 8 plus 1. So that's 6 over 8, 13, so 18 over 8, which is 9 over 4 plus 1, so that's 3 1/4. 3 1/4 or 13 over 4. So that's the expectation. Now when you get a game like this, that's the expectation, that's the expected return. So when someone plays this game, they expect $3 1/4 in return. Now they're costing $5 to pay. So the game costs $5 to play, and so $3 1/4 is less than $5. Therefore, the game is not fair. Game is not fair. Now, when we talk about fair, we're talking about the fairness in the idea of the structure of a card game or whatever like that, or any game that you're playing, like people playing chess against each other. That's fair. But you don't expect prize money to be fair, but you do expect a certain amount, and that's not bad actually. I think when you go to the slot machines and stuff like that in Las Vegas, they give a return roughly of about 70%. So you don't expect it to be fair. But basically, if the expectation of a game is exactly equal to the cost of the game, then that's what we call fair. But that commonly it will be less. So $3 1/4 is less than $5. So the game is not fair. Okay, so can you complete the rest of exercise 7J, please? Thank you very much.